We are happy to present our work titled Manipulability Optimization for Multi-Arm Teleoperation at this year's International Conference on Robotics and Automation. In a time where robots are becoming more and more autonomous, we briefly want to motivate our work in teleoperation. Being able to remotely operate a robot or a system of robots can be desirable in situations where human intervention is necessary, but human presence is undesirable due to a hazardous or difficult to access environment. It can also serve as an augmentation of human capabilities, for example increasing human strength, speed, or capabilities related to repeatability and precision required by a task. And even in cases where full automation is desirable, human input in the form of teleoperation can still serve as a teaching example or as one way of interacting with a collaborative system. Having established why one would like to teleoperate a robot, we can now have a look at some of the limitations or open research questions related to teleoperation. While some robots can be built to match human anatomy as closely as possible, they are in general very complex and expensive. Furthermore, not every human has the exact same anatomy. An active field of research is therefore concerned with mapping human input to a robotic arm with a different structure in a way that makes the operation feel intuitive and makes very precise teleoperation possible. This is related to the next question. If we can figure out an intuitive mapping to a robot arm, can we come up with intuitive ways of interacting with a group of robots, similarly to an interaction between experienced construction workers, movers and packers moving heavy pieces of furniture while being guided by a colleague, or athletes reacting to their teammates' movements in order to position themselves? A third limitation comes from the technical aspects of rigid robots. How can an operator deal with workspace limitations or internal singularities of the robotic system, which do in general not map to the operator's experience? This aspect is also highly related to the safety of such a system, as interactions close to the system limits can lead to unwanted abrupt or high-velocity movements. In our approach, we try to address some of these questions. In order to interact with a group of robots rather than with a single robotic arm, we model the system as a payload that all robots carry collaboratively. The attachment points to that payload are modeled as handles, around which the robot arm's end effector has one unconstrained rotational degree of freedom. The payload pose, and thus the position and orientation of each handle, are governed by a user via a VR interface. With the increased availability of high performance and relatively cheap headsets and 6 degree of freedom controllers, virtual reality has become a reliable and intuitive input method. The operator can grab and move the virtual payload either directly or from a distance, and move around the system in order to make adjustments from different angles. The state of each robot arm is then computed in order to match the operator's input as closely as possible. This unburdens the operator from having to worry about the low-level movement of each arm and enables them to focus on higher-level tasks. By giving the robot arms an additional degree of freedom that is not locked, we can additionally optimize for a secondary objective. In our case, we will try to improve the pose of each arm by improving the manipulability index. Since Yoshikawa's introduction of the manipulability as a kinematic performance measure in the 80s, a lot of work has been done that makes use of the index or the singular values of the Jacobian in order to avoid singular configurations of a robot arm. Predicting when singular configurations are close can be useful in order to block further movement of the arm towards a singularity, for example by means of a virtual force field pushing the operator in the opposite direction. This is very useful for physical human-robot interaction. In our case, we do not have physical feedback for the operator, but we can still try to optimize a robot arm's configuration according to a similar principle. Regarding VR teleoperation, there has been an acceleration in research work with the rise of headsets such as the HTC Vive or the Oculus Rift and Quest. Different approaches exist on how to teleoperate a robot, for example through embodiment, where the operator takes control as if the robot's body was their own, or through solutions where the operator guides a robot arm while looking at the real system from a third-person perspective. An interesting example where the operator can switch the point of view from the robot's head to a camera on the robot's end effector for more precise movements was developed by Chen et al. A recent interesting control scheme where a virtual plane is used to map the operator's input to an arm has been presented by Li et al. As recent as last year. As shown in Rakita et al., such input methods via 6 degree of freedom controllers can greatly increase the speed with which an operator can achieve a task compared to a force feedback stylus or an input screen. Interactions between multiple robot arms introduce many constraints, which makes it harder to control these systems. An interesting approach for a handover of an object from a human operator to 2 robot arms has been developed by Stelian et al. And Xian et al. Presented a method which considers regrasping of pieces of an IKEA chair for autonomous assembly, dealing with workspace limitations and closed-loop constraints. While these systems are not necessarily teleoperated, they could serve as an example of what an ideal system of collaborative robot arms should be able to achieve. The degree to which a human can help and guide the system is a question that is at the core of our research interests. Here we show an overview over our current system. An operator wearing an Oculus Quest headset interacts with a virtual environment via 1 or 2 6 degree of freedom controllers, or alternatively their hands, using the onboard hand tracking capabilities of the headset. The operator can freely move and rotate the payload by holding the trigger button of a controller, or by forming a fist as a grab gesture when using hand tracking. The movement of the payload is then wirelessly transmitted to a server, which solves the inverse kinematic problem and runs our manipulability improvement. The resulting robot poses are then transmitted back to the VR headset, as well as to the real robotic system. We will talk more about this in the future work section. We formulate our problem as a constraint optimization problem, in which we minimize the squared error between the current forward kinematic solution k of q and the desired end effector pose x. This error ignores the rotational term that corresponds to the free rotational degree of freedom around the handle. Similar to Dimeas et al., we then compute an update step along both directions, corresponding to the free rotational degree of freedom scaled by a factor delta t, which ideally corresponds to the duration of an update step of our method in order to keep the solution close to the IK solution. In the case that moving along one of the directions, indicated as a plus or minus, improves the manipulability index by more than a minimum threshold theta, we give the corresponding solution q prime to the IK solver as an initial guess for the next iteration. We test our method on 3 different trajectories, a predefined circular and square trajectory, as well as a pre-recorded VR trajectory. We test the method on a system comprised of 3 UR5 robot arms, as well as a system of 2 2-armed Yumi robots. It can be seen that we are able to improve the average manipulability for all trajectories, and that in most cases we are even able to improve the average positional error. Our results are especially encouraging in the VR trajectory case. In a more in-detail look at the manipulability evolution over the course of the trajectory, we can see that indeed the arms generally tend to fall less drastically into regimes of low manipulability. The same can be seen for the system of 2 Yumi robots, although there seems to be an instance where the right arm of the first Yumi cannot completely avoid a singularity. It falls into that regime later and is able to at least improve the manipulability at a low value before moving up into a more favorable regime again. Finally, here we can see that the system initially starts out with a lot of end effector offset and cases of 0 or close to 0 manipulability, but that it is gradually adjusting to a more favorable regime, which leads to a smoother and safer movement thanks to our method. We have introduced an intuitive interface for VR teleoperation of multi-arm systems, which is flexible in regards to the number of robots and their type, as indicated by a small test that we did with 10 UR5 arms. The method is computationally lightweight and requires little tuning, but it is able to improve the average manipulability of the system reliably. The current limitations of the system are that the manipulability improvement step can violate the inverse kinematic solution due to higher order errors. In cases where this error is too high, the inverse kinematic solver will probably disregard the initial solution and find a solution with lower manipulability but smaller positional error again. Because we optimize each arm individually, we can also not give any grasp guarantees. Improving our method to address these issues is therefore an important part of our future work, as are experiments on real hardware. Since the acceptance of this paper, we have been able to achieve both of these goals already, and the publication on the update is currently under review. We would also like to extend our approach to robot arms on mobile bases to enable more real-world examples for collaborative transport and assembly tasks. Thank you very much for your interest.